Good morning. Let's get started on time. We have a busy day today. Okay, first of all, those who turned in your sheets from the seminar, thanks. If anybody else has them, you can turn them in to me as you're leaving, or the TAs, whoever you happen to see. So the rules on when you have to turn those in is you can turn it in to me or the TAs anytime you can find us. Office hours discussion is fine. But it turns into a pumpkin 1 week after the seminar you attended. So you can't save them up for the rest of the quarter. You have to turn it in promptly. Usually I'll be at the seminar. Yesterday I had to skip it because I was working on an NSF proposal that was submitted today. But usually I'll be there and your TAs will probably be there. Okay, so I think last time I said that the material from today's lecture was going to be on the exam. I changed my mind. When I started making up the exam, we've covered a lot of stuff. So I'm glad you're happy about it too. So the stuff from today's lecture, I think it'll actually help you understand some of the material that's going to be on the exam, but it itself is not going to be there. Does anybody have any questions about the exam or extra credit or that kind of stuff? All right, good. Let's continue talking about diatomic molecules and selection rules. Okay, so last time I briefly showed an anharmonic potential, and we were kind of running out of time, so I didn't talk about it very much, and I got a few questions about it. All right, so there's a problem on how to deal with anharmonic potentials and looking at the correction for the fact that your diatomic molecule is not a perfect harmonic oscillator. That's in the homework. It's good to do. It's good practice. What I want you to know about it right now is really conceptual. Okay, so if we have the harmonic oscillator potential, that's just a parabola. And so that means as you go up to higher and higher energy, there's this potential extends forever. And so what that would mean in a physical sense is that your diatomic molecule is vibrating, and of course the vibrational states are quantized, but when you put in more energy and kick it up to the next state, it vibrates faster, and then on and on. And if it were a perfect harmonic oscillator, no matter how much energy you put into it, it would just do that forever. It would vibrate faster and faster, but nothing would ever happen to it. Of course, in reality, we know that's not true. If you put in enough energy, there's some threshold, which is the dissociation energy, above which the molecule just falls apart. It has so much vibrational energy that the nuclei just fly apart and go off into space. And so that's what the anharmonic potential is telling you. So first of all, we have this funny shape to the potential, and that energy where you go over the little threshold is the dissociation energy. And another thing that you notice is that the levels get closer and closer together as we approach that dissociation energy. So that's all I want you to know about it right now. It's just at a conceptual level what's going on with it. And again, there is a homework problem about it where you have to look at it more quantitatively. It's good practice, but right now, if you understand this, you're in good shape. Okay, so as promised, now what we're going to do is we're going to go through the gross and specific selection rules for vibrational spectroscopy, IR spectroscopy, and for rotational Raman. And this is going to tie together a bunch of things, hopefully. So it's going to tie together the threads between looking at spectra of diatomic molecules, looking at their vibrations and rotations, and also talking about symmetry, and in particular, the things that we've talked about with the even and odd rule and integrals going to 0 because of symmetry. And the plan is for this to give you a little bit better idea of how you use this. Okay, so we know how to state the gross selection rule for IR spectroscopy in words. The molecule has to change its dipole moment when it's vibrating in order for that vibration to be IR active, or for us to observe the spectrum. So let's translate that into math. So what that means is that we have this value of the transition dipole, and that needs to be not 0 in order for there to be an IR active mode. All right, so remember your Dirac notation. Here we have in the ket nu I, that's the initial state. And then the bra is nu F, that's the final state. And we're looking at a transition probability between them. But here we're saying that those states are connected by the dipole moment operator, which is mu. And of course, we have to remember our terminology in context. Mu is sometimes a reduced mass. Here it's not. It's a dipole moment operator. OK, so if we think about what our dipole moment looks like in a little bit more formal way, it comes from having two partial charges, and I'm calling them plus or minus delta Q on opposite sides of the molecule. We're just going to assume it's diatomic and polar for the sake of making the problem easy. And it's separated by some distance r. So r is your equilibrium radius between the two molecules. And at some point in time, it also has some displacement x that's due to the vibration. So RE is the equilibrium distance between the nuclei, and then x is your displacement as it's moving around. OK, so the dipole that we have at any point is the radius, or the distance times the charge. And so that's RE times delta Q plus x times delta Q. So we have a term that's going to stay with us that has to do with the equilibrium distance. And then we also have this little displacement. And the term that's always going to be there at equilibrium is called mu naught. So that's the time-independent sort of standard dipole moment of the molecule that you've seen before. And that's going to be a constant. So it's just the value of that operator evaluated at that distance. OK, so now let's look at what happens when these states are not equal. So we're making a transition. Nu initial is not equal to nu final. And here we can plug in what that dipole moment operator represents. Remember, we're just talking about a linear diatomic molecule. All diatomic molecules are linear. So we only have a one-dimensional coordinate. All it can do is vibrate along this axis that we're calling x. If we had a more complicated system, we would have to break this out and do it in all three directions. And we're going to see that in the case of rotational spectroscopy, where we look at the polarizability. But for this case, we can simplify it a lot because we're constrained to be in a one-dimensional system just because of the setup of the problem. It's just a vibration in one direction. OK, so my dipole moment operator just gets replaced by x. That's the only component of the dipole that we're looking at. And so I can evaluate that. And so we get that Q is just d mu dx. And if we just look at that, we can see that that's going to be 0 unless the dipole moment is varying with displacement. Yes?
If you said Q equals that, if you plug that in, where does your delta go? Is it delta Q equals that?
Yes, sorry. Hopefully that's the only one. There's a lot of math today. OK, so we can work this through. And it takes a little bit of getting used to the notation. But hopefully you can see relatively straightforwardly where this argument comes from. So we're translating this statement that we can already see how it works into the math. OK, so that's the gross selection rule. That tells us that the molecule has to have a dipole moment, and sorry, I should be more careful with that. The dipole moment should change as a result of that vibration, and that's what gives us the IR spectrum. So now let's talk about the specific selection rule. So the specific selection rule, remember, is the statement that we can only change vibrational states by increments of plus or minus 1. All right, so to start to think about how this works, remember what the harmonic oscillator wave functions are. They're the Hermite polynomials, which have these kind of functional forms. They're in your textbook in the early chapters. I think maybe it's chapter 3. If you need to review what those look like, it might be good to go check that out. But here's what they look like sort of plotted out. And one thing that we need to remember when we start talking about the selection rules and how we know whether we can get a transition between one or the other is the even-odd rule. So if we look at these just without even seeing them mathematically, we can see that the symmetry changes every other state. So this one is even, the next one is odd, the next one is even, the one after that is odd, etc. And remember, if we integrate an odd function over a symmetric interval, that integral is going to go to 0. And we also know that if you multiply two even functions or two odd functions together, you get an even function, and that doesn't go to 0. But if you multiply even and odd, you get odd, and it does. OK, so what does this have to do with our selection rules? We have to look at what happens when we plug in our dipole moment operator in between those two states. So we're going to be integrating over a pair of states connected by that dipole moment operator. And we're going to look at whether the resultant is even or odd, and that's going to tell us whether there's a signal there. OK, so before we do that, I just want to point out, here's what that looks like for an anharmonic potential. The picture I found, only the even states are drawn in, I think just for clarity, but you get the idea. So here's just what that looks like in a more realistic potential, but the argument is the same. OK, so we're back to having our transition dipole. And again, we know what that is. We've got an initial state and a final state, and they're connected by the dipole moment operator. And so now, in order to figure out what we're doing, we have to actually write down the wave functions. And so we go look them up in our book or look on the Wolfram site and find out what the Hermite polynomials are. And they're written in terms of this term alpha, which is not the polarizability. Again, we have to pay attention to context. So here are Hermite polynomial functions. And again, we replace our transition dipole with just x, because we're still talking about the harmonic oscillator. We just have displacement in one dimension. That's all there is going on. OK, so just to remind you how this works, I wrote this out in the long version, so not Dirac notation. And you can start to understand why people who do quantum mechanics for a living like to use Dirac notation. It's really compact. It's nice to not have to write down all these integrals all the time. Of course, the trade-off is you have to make sure that everybody knows exactly what you're talking about, because there's a lot of ambiguity that could be hidden in the notation otherwise. But so here, we're talking about the well-defined case of a harmonic oscillator. We all know the wave functions. We can look them up, so that's OK. All right, so if we work out this integral, we can pull out the constants. And we need to know an identity relating to Hermite polynomials. And again, we don't have time to go through this, but you can check it out on the Wolfram Mathematica website, or resources like that. But so here's a nice identity involving Hermite polynomials that's going to help us evaluate this integral, or at least simplify it in a form where we can see what it does. OK, so having rewritten this sucker in the form that this identity gives us, I swear that's going to do something useful for me in a second. We need to use another identity in order to get there. This integral equals 0 if nu prime doesn't equal nu. Again, where did I get this? I looked it up. And one of the things about going through these kinds of arguments, when you're first learning how to do it, you really wonder, how does anybody think of this stuff? Or when do you know when to do what? It takes a lot of trial and error. I mean, so I'm running through it here in lecture, we don't have very much time, it's all nice and neat. If you actually want to work out stuff like this for yourself, starting from scratch, and if you don't know the answer, it takes a really long time, and there's a lot of trial and error. So if it doesn't immediately seem trivial, that's completely fine. That's because it's not. OK, so this identity equals 0 if nu prime doesn't equal nu, and it equals this function of nu if they are equal. And so that means the first term in this whole thing equals 0 unless the final state equals the initial state minus 1. The second one equals 0 unless you jumped up by plus 1. And so we get the fact that the transition dipole equals 0 unless our change in nu is plus or minus 1. So it's called the specific selection rule for a reason. It's very, very specific. You have to plug in the actual functions for the wave functions here and look at these integrals in great detail to see what's going on. So anyway, now you know where that comes from, and you see how our symmetry arguments and being able to use the even-odd rule and decide which integrals go to 0 by symmetry can help us out in looking at fairly complicated things. So here it's nice because we happen to know this identity, so we can actually get the value. But even without having the value, you could say, from symmetry arguments, this is either 0 or it's not. All right, there's one last thing that I'm not going to spend a lot of time on right this minute. We'll come back to it later. I want to point out that there are some spectra for which you do see a peak in the middle of the spectrum. So I just spent all this time proving to you that you don't see a peak in the middle of the spectrum ever for a reason. But it turns out if your molecule has orbital angular momentum, so that means not all your electrons are paired. In other words, it's a radical. Then you can have a transition delta J equals 0. And so remember, we have, on this side of the spectrum, we're going from 0 to 1 in the vibrational state, and J to J minus 1 in the rotational state, the opposite on the other side. And we just proved that for a normal diatomic molecule, it's illegal to go from 0 to 1 in the vibrational state and stay the same in the rotational state. However, if you have orbital angular momentum, this is allowed. And we're going to talk about why later on when we talk more about electronic structure and electronic spectroscopy. But I just want to point out that this is there. One of the things that a lot of people find hard or frustrating about chemistry is that there are lots of rules that are given, and then later you find out all the exceptions to the rules. Well, we told you this, but it's not entirely true. I want to point out those things up front, that we're operating under a particular set of assumptions, and we're using some rules that apply to specific cases. They're not universal. There are other cases. We'll talk about that one later. OK, so now we have gone over our selection rules for IR spectroscopy, and we're going to talk about Raman. Question first.
Yes, just to put everything in perspective, all these selection rules and things go into like designing the IR machine, or what is it? What do you use this for?
What do you use this for? That's a good question. So designing the IR instrument is another whole area of research that actually we have some really advanced researchers at UCI doing this. Professor Ge designs new IR spectrometers. Hopefully we'll get a chance to talk about some applications at the end. But why do you need to know the selection rules? So imagine that you made a new molecule and you don't know its properties, and you get its IR spectrum. We need to be able to interpret that in terms of which levels are we looking at. So everywhere we see a peak, that represents a transition between one level and another. And if we don't know, like, can we only go up by 1? Can we go up by 2 or 3 or 4? Then we wouldn't know what that spacing represents. We wouldn't be able to interpret the spectra. And so that's why we need to know these things in order to look at the spectra. And so if you're a physical chemist working in this area, there's a really tight connection between theory and experiments. So you go do the experiments in the lab, and then you have to work out the theory to explain why your results look like they do. And sometimes that's done by the same groups. Sometimes that's done in collaboration. So I'm an experimentalist, but I have collaborations with people like Professor Tobias, who does theory, and then some other things we work out ourselves. But it's always really important to understand the physical basis for the stuff that you measure. OK, so that was IR. And again, I want to emphasize, remember our whole lecture about the differences between absorption and scattering. Don't get confused about the difference between IR and vibrational Raman spectroscopy. They have a different physical basis. In IR, we're talking about absorbing a photon and going up in an energy level. In Raman, we're talking about a photon being scattered and either giving up or getting a quantum of energy from the molecule. OK, so right now, we're going to talk about rotational Raman. So we just talked about IR spectroscopy, which is direct vibrational spectroscopy. Now we're talking about Raman, which is scattering, and we're also talking about rotations. OK, so let's think about a molecule in an electric field. And again, remember in words our gross selection rule for rotational Raman. When the molecule rotates around, the polarizability has to change with time. Otherwise, we can't see anything. And so again, mu is our induced dipole that's induced by the electric field. But now we have a more complicated situation. It's not a one-dimensional problem. We still have a diatomic molecule, but it has this three-dimensional electron cloud that's shaped like a football. And it has components in all three dimensions. It's a second-rank tensor. So we have to break down our mu into x, y, and z components. And so here's what these are. And again, if you're not quite comfortable with where that came from, go and review conversions between Cartesian and spherical coordinate systems again. So, and here I'm being a little bit careful to try to call it mu induced, because this molecule may or may not have a dipole on its own. It's got one induced by the electric field, and that's what we're interested in rotational Raman. OK, so this thing has an x, y, and a z component. The electric field also has an x, y, and z component. So we're applying our electric field in whatever direction, and it's got components in each dimension. OK, so then what it makes sense to do is to split up my induced dipole in terms of the polarizability contributions from the parallel and perpendicular orientations of the molecule. So remember, we said, to a first approximation, it doesn't matter whether the molecule is pointing like this or like this. It just matters whether it's parallel or perpendicular. And so we can rewrite that in terms of alpha parallel and alpha perpendicular. So remember, alpha here is our polarizability, and it's time dependent. It's going from parallel to perpendicular twice every rotation. And so we can simplify this expression for the induced dipole. All right, so again, remember, the point of why we're working through this is that we want to see what happens to the transition dipole. So that is, the transition is allowed, or the molecule shows us something in the rotational Raman spectrum only if the transition dipole is non-zero. So here's the transition dipole. We have quantum numbers for our rotational states, and we have the x, y, and z component of the induced dipole sandwiched in between. So again, we've got our final state and our initial state, and it's connected by the operator. And the operator in this case is this transition dipole that is an interplay between the polarizability of the molecule and the applied electric field that's coming from our spectrometer. Yes?
The J and the MJF, that's the thing, those are the quantum numbers for the angular momentum.
That's right. J and MJ are the quantum numbers for the angular momentum. And I put both of them in here to, to make it general. Yes?
Is the bottom one supposed to be FIZ?
Yes. Thank you, sir.
Can it be any direction that just has to be, if only, like, say, only x has a value, but the rest are 0, is that still forbidden?
That's a really good question. So, the question is, do you have to have a component in x, y, and z for it to be allowed? No, if any of them is allowed, then it's allowed. You'll see a spectrum. Okay, so here's our induced dipole again. And see, we again hid our wave functions with the Brockett notation, which looks nice and clean. Now let's go back to what the wave functions for a rigid rotor are. They are spherical harmonics. And they're kind of big and ugly, but you can see their symmetry easily enough if you plot them. So again, this is something to look up if you need to do it. Go check it out in the early chapters of the book or on the Wolfram website. Okay, so here's some spherical harmonics, and we can use a trig identity to simplify our expression for the induced dipole in this case. And so if we're looking at the transition between two rotational states, it has two components. One has to do with the polarizability, and the other one has to do with the electric field. And so this part goes to 0 unless delta J equals 0. So this is the one that contributes to the Rayleigh line. So this is the no transition in rotational energy. That photon hits it and it just bounces off elastically and it doesn't change frequency. And so if you're doing this experiment to find out something about the molecule, this is really boring. So you shine your laser at it and the same color laser light comes back off, and that's all you get. The other one goes to 0 unless you have a change in rotational state of plus or minus 2, and you have to have an anisotropic polarizability. So that delta alpha has to not equal 0. So between parallel and perpendicular, you have to have a difference in alpha. Otherwise, this whole thing is going to go to 0. Yes?
You have JF equals JI there and JF equals JI. Would that be JF equals JI plus 2?
JF equals JI plus or minus 2, and delta alpha does not equal 0.
Does not?
Right, because if the change in polarizability equals 0, then that term is going to go to 0 right away. Just making sure everybody's awake. Thank you very much for catching them. Okay. So we can put this in terms of an integral involving spherical harmonics, but you get most of the take-home message just by looking at this. Okay, so just for completeness, here's what you get if you write out the x and y components. This is not, the details are not the most important things to know right now, but I just wanted to write it out for completeness. Okay, so now that we got through the selection rules and we understand where they come from, let's talk about how this actually gets used in a practical sense. It can be hard to make the connection between the examples that are simple enough that we can work them out in class and what you would actually do in a research context. Okay, so one of the things that IR and Raman spectra are used for most frequently is identifying functional groups in organic molecules. And as you can see here, so here's a pair of spectra of styrene and butadiene rubber. So this is a real material that somebody made, and they're interested in knowing what's going on in its structure. And I want you to notice a couple things about it. So one is there are these peaks in the IR and Raman. They're plotted on the same scale. So here we have this in wave numbers. It's given as Raman shift, but the IR one is on the same scale. And so a couple things to notice. Some of the IR and Raman bands coincide. So you'll see some vibrations that have a transition in both the IR and the Raman spectrum. Just like when we do our symmetry analysis and we come up with some of the vibrations of the molecule are IR active and Raman active, and some of them are one or the other. So we see, for instance, this set of transitions is really strong in both. But if we look at this one, that has a big peak in the Raman spectrum and only a teeny tiny one in the IR. So what that means is, we have some vibrational mode that really changes the electric polarizability a lot. It means there's a large overlap between those two states when they're connected by that polarizability operator. But in the transition between vibrational states, it doesn't change the dipole moment very much. So again, these symmetry arguments alone don't tell us anything about the magnitude. It just tells you whether there's a peak there. But you have to actually plug in what the values are and calculate the intensities if you want that information. So you can have something like this, where there's a huge value in the Raman and a tiny little one in the IR, and symmetry will just tell you that they both exist. That's it. Other things that are useful to know here, for really complex molecules, a lot of times, so for instance, if you're a synthetic chemist, it's not really worth the effort to fit every single band in the spectrum and really understand everything about all the details. Physical chemists like to do that, and that's an important part of P-Chem research, trying to understand why things are the way they are. For synthetic chemists, though, this is still incredibly useful, even if you don't go through and fit everything, because people have really well documented tables of where bonds belonging to certain functional groups show up in the spectra. And so you've probably used this in lab, or some of you are doing synthetic research. You can use it to just see what kind of functional groups you have in your molecule, and it's very powerful. Here's another one that's even more complicated, where somebody has assigned what types of bonds are likely to vibrate in these regions. And so again, you see things like the CO stretch shows up in both, but it's a lot more intense in the IR than in the Raman, which kind of makes sense. If you think about a carbonyl that's stretching out, that is going to change the dipole moment a lot more than it changes the polarizability. So some of them are easy to visualize and rationalize, some of them less so. If you actually want to get into all the details and see how this works, you have to do it computationally. And people do have pretty good success predicting these things and understanding all the modes computationally. A good example of somebody who does this for research is Philip Furch at UCI. So that's something that his group does. There are many others in different places. OK, so what else can we do with vibrational spectroscopy in a more advanced context where we're really interested in the physical chemistry? This is an example from the website of Charles Harris and his group at Berkeley. And they're illustrating how we can use vibrational spectroscopy in a time-resolved way. So instead of just taking a spectrum at a particular point in time and measuring the bond vibration, they're interested in looking at some chemical process that's happening and using fast laser pulses to capture snapshots of the system as it's undergoing some kind of a change. And so here's their schematic picture of what that looks like. There's a chemical reaction, and it's going between different states throughout the course of the reaction. And they're able to probe this thing with an IR pulse and look at it at different time points and actually watch bonds being broken and formed. So they have their IR spectrum, and as they watch it as a function of time, they can see vibrational modes corresponding to one set of bonds disappearing and another one growing in. So you can actually use these kinds of things in a time-resolved way to learn something about processes that are happening in real time. So that was an example from Berkeley. Here's an example of another IR application from UCI. So this is from Professor Gu's lab. One of the things that she does is two-dimensional IR spectroscopy. So in this case, we have our IR spectrum that is, so basically each of these two dimensions is a correlated IR spectrum. And what that gives us is something that looks like a topological map when we're looking down on it. And we're going to talk about this in a lot more detail as far as how it actually works when we get into two-dimensional NMR. But for now, just treat it as it's two IR spectra that are correlated to each other. If you took a slice through vertically or horizontally, you would see the normal one-dimensional infrared spectrum. And what you get by doing this in a correlated fashion and looking at it this way is you see connections between different vibrational states. And so what that is telling us is that for a large complicated molecule like this peptide in solution, if you have one bond vibration somewhere in the molecule, it's not completely independent from everything else. If you wiggle this bond over here, that's going to affect how one on a different part of the molecule vibrates. That's what these peaks are telling you. They're correlations between pairs of vibrations. And so by looking at that, you can learn interesting things about the molecular structure, how it interacts with the solvent or its environment, and also how it changes over time. Okay, so here is our grand summary for vibrational and rotational spectroscopy. We're, for the most part, done talking about it. This enables us to learn things about molecular geometry for simple molecules. We can identify functional groups and figure out what bonds are being destroyed or formed for more complicated ones. And of course, we can look at things that are as complex as all the way up to proteins. But in that case, we need a lot more sophisticated computational methods to be able to fit the data and understand what we're seeing. And for those of you who are interested in doing research, these are the groups that are doing vibrational spectroscopy research at UCI. And I'm sure that I forgot at least one group, but here are some examples. Yeah, I forgot Professor Nizhgorodov. That's one. And as I mentioned, Professor Furch looks at theoretical modeling of different kinds of spectroscopy, including but not limited to vibrational spectroscopy. So yeah, of course, I couldn't do that without forgetting someone. All right, so we are done a little bit early today. That's because I'm going to stick around and answer questions. Good luck on the exam. Oh wait, one thing I want to announce. For those who didn't see this, John Mark is having a review session this evening. It's 8 to 9:20 p.m. and it's in Roland Hall 104. Is that right, John Mark?
Sounds right, yeah.
Okay, cool. TAs, can you guys stick around for a minute after class? All right, we're done. Don't forget to check the seating chart tomorrow night and make sure that you're all ready to go and set up for the exam.